So, good afternoon. It gives me pleasure to introduce two of my esteemed colleagues, Prof.Gururanjan and Prof.Prita. Both of them are from Material Science and Metallurgy Department. Prof.Gururanjan has done his BSc MSc from Madras University and Pune University, followed by MSc by Research in ISC Bangalore, and his PhD from again from ISC Bangalore. This was in 2006. He works in computational material science, phase transformations, microstructural evolutions, thermodynamics, and phase field modeling. Prof.Prita also joined around the same time, Metallurgy Department in 2006. She has taught in various undergraduate and postgraduate courses in Metallurgy Department, largely in the area of mechanical behavior of materials, computational material science, and she has been also associated with teaching communication skills to postgraduate students. So both of them together have been teaching this computational lab. It's a unique way of teaching, and I'm happy that they are agreed to share their experience.
Thanks, Sachin. So my name is Gururanjan, and that is Professor Pant. And we want to talk about a lab course on computational methods, which we used to teach. We taught for quite a while and handed it over to other colleagues now. Professor Pant has been associated with the course from the very beginning. It was designed by her and another colleague of ours, Professor Saurabh Mishra, and they also built the computers and the lab for it, along with one Professor Sirish Wagulde. So these three were involved in actually setting up the lab itself, and I came late to the party. I joined later. But as you know, people who came late to the party are the ones who enjoy the most. So I had lots of fun teaching the course. They did all the hard work, setting up the computer, buying it, running through all the tender process and working with the carpenter and getting the civil work done. So it was a nice, good experience I had. So how many of you have taught a lab course? Okay, about 60%? Okay. So rest of you don't have an option of teaching a lab course, or you don't want to teach a lab course? How does it work? Why is it there are some who haven't taught a lab course? Lab course. A course for a semester where people will come to the lab and they will do, and you are the instructor for that course. Okay. Are there people here who have never taught a lab course?
A lab or a lab course, whatever you want to call it. Everybody's taught it. Yeah, I have a course.
Yeah, yes. Yeah.
So if you taught both theory courses where you walk into a classroom and sitting there and give a lecture, and a lab where you come into a place where there are instruments of various kinds and students are expected to work with their hands and then do something with their data, or in that case they are supposed to work with their hands but on a computer. Which one did you enjoy more? So people who enjoyed the lab for teaching the lab more should raise their hands first.
Okay, good fraction.
So I assume the rest all enjoyed teaching the theory more compared to the two.
Okay, so the first point I was trying to make is that all this active learning has always existed, especially in engineering colleges, that every afternoon you have to go do a lab, and that teaching was active learning exercise. Having said that, there are two groups of people that I have found, and these two groups are like flame wars on internet. They strongly believe in the philosophy of teaching the lab course. Each think that the other party is stupid, only they are right. And when you are sitting down to write syllabus or trying to design courses, it can become quite heated, let us say. Okay. So now I don't know what the philosophy of lab course is in the places where you teach. So is it that, for example, the lab course should be concurrent with the theory course? In most of the places. So are there places where you will do the lab first and then you will get to know about why you did or what you did or how you did later? Theory is always first? Okay. I belong to a minority who think that we should not teach them the theory first. I believe that we should let the students go, do things, and this is coming back to what Sachin kept talking about. You should make them face the problem first before telling them why. We are spoon feeding them by telling them upfront, this is how it is done, and then sending them to the lab. We should not do that. We should not teach them any theory. Safety, yes. What are the things that are allowed in the lab? Yes. How you should deal with an equipment? Yes. After that, you should actually make them do and ask them to explain why or how or what is happening, and then send them to a theory class. Probably they will pay more attention. Okay. So this is, like I said, it's a philosophical point. There are people who strongly believe that without teaching them theory, don't allow them to step into the lab. Yes, sir.
No, it's not like that, sir.
Huh.
From where we are teaching right now,
Right.
there is a serious problem of infrastructure.
Right.
That's why all have says like that they believe in this and they didn't believe.
I see. But they do believe in making students do first.
They think so, but that's the main reason nobody is there.
I see. So let's also keep it very discussion based, active, and I don't have as many slides as Sachin, so we have to fill 1.5 hours. You have to also participate. So how many of you think that if there is enough facility available for you, for example, I mean, in some courses I cannot think how you can make them do the lab without teaching them. Maybe the computer programming you want to teach, you want to tell them about some structures, some loops, some for while, etc. before throwing them a computer problem, right? Okay, factorial, write a code, but you have to tell about some for loop before doing that. That part I understand. But there could be labs like in maybe mechanical engineering or in our thing metallurgy, where you can make them do and then make them observe, make them wonder why something is happening and make them go back and look at this thing, because that gives the so-called roadblock to them first and makes them pay attention, makes them think about, and sometimes they can come up with their own solutions. This was some other discussion we were having, and even programming things, I am saying that you have to teach first before they do, but somebody was telling me, Professor P.V.M. Rao, I think, Delhi. In second year, they allow their undergrads to actually do a project for very small credit, some 2 credit or something. But it has to be necessarily outside of their subject. If you are a mechanical engineer, you have to pair up with somebody from some other department, electrical or materials, and do a project. And they found that without actually teaching, these students were doing things that they haven't even been taught in the classroom. And they were first surprised. But then they found that there are lots of resources that are available, and when the student knows that this is what is needed, they go actually learn. So he was telling, you can't stop anybody from learning. You can't say, till I come to programming, you can't do programming. That's not how it works with the student. So even in those cases, it might be possible today for you to have the lab first and then go to theory. But is there anybody else who thinks that if resources are available, we should allow them to do the labs first? Yes? Yes? Some at least. Okay. So good. So this course is one such course where it is taught to second year students. These are undergrads who finish their first year, where they do all math, physics, chemistry, biology, computer programming, and the labs in physics, chemistry, etc., and workshop. And then come to second year. In the second year, in the second semester is when we teach this course. And there are other computational courses like Sachin was mentioning. There is a data analysis and interpretation course that they would have done in the second year, first semester. And they also have a numerical methods course, which the math department used to teach or still teaches, but in the new curriculum it will also come back to us. So there is a numerical methods course. In addition to that, there is this lab course. Both data analysis and interpretation and numerical methods course are theory courses which have a component of tutorial or lab depending on the instructor. Okay. According to curriculum, it is 210. The data analysis and interpretation is 2 lectures, 1 tutorial per week. And the numerical methods is 310, 3 lectures and 1 tutorial per week that they have to do. Okay, it's a 8 credit course. But this is a course which is completely hands-on, no theory component at all. According to the syllabus, it's 003. That is how the credit is given. And because we have a very large class of about 120 students, and the classroom we had was only about 60 computers, so the students come only once in 2 weeks to the lab. So we run on the whole about 6 to 7 lab sessions. That's all we teach them. But unlike other lab courses, even in IIT it is true that we have a resource problem. In many traditional labs, you will see groups of 3, 4 or 5 doing one experiment. And that always has the problem that, one person is enthusiastic in doing, the rest of them are just standing around. And then they lose interest pretty soon. I have heard that in microscopy class, the student they are supposed to look through the microscope, look at the structure and draw it in their report. So instead of looking through the eyepiece, the person was just taking a photograph, looking at it and drawing. They become completely disconnected with the lab if they are in a group where the entire group is not participating in the experiment. There are lab experiments where the group has to participate. I was also part of another lab where they have to melt about 20 kilograms of steel and then pour it. It requires a few people and lots of physical labor. So the group works together, everybody is involved. Those are different. In other places where they are not participating completely, if you put them in groups, they don't perform that well. So we decided that in this lab, each person will get their own terminal and they will work with the problems that is given to them. So that is how we run this lab. We ran this lab for several years. So now we have taken a break from teaching it.
So I'll tell you a little bit about the genesis of this lab. Basically, this lab was unusual in the sense that, so we are a metallurgical engineering and material science department. And our undergraduates, they themselves felt that their grounding in sort of computational methods was not as good as, say, for instance, somebody in an electrical engineering department gets. So the students wanted such a course. And the goal of the course was not to teach them programming. They've had a course in programming in their first year. The goal of this lab course, and that was the reason it was also a lab course, is to teach them how to use available computational tools. So we selected Matlab and Octave. Octave is a freeware, so it's very nice if you select Octave because students can download it. If they have their own computers, they can use it in their own time. With Matlab, you're still constrained with the availability of licenses. Okay? And the two are almost the same, except for 1 or 2 functions, which Matlab may have and Octave doesn't. But for the purposes of an undergraduate course, the two are identical. So we decided to make them comfortable with using these 2 tools. And by making them comfortable, our goal was that as they go through the rest of their years of engineering education, if somebody gives them a problem, for example, they take Sachin's course in their 3rd year and he says, okay, go do this fit and plot the residuals and then try to see what sort of a distribution it is, they should feel comfortable sitting in front of a computer, opening one of these things and writing a small program which will do this for them. So the idea was introduce them to how Octave or Matlab works, do a lot of hand holding in the first couple of sessions, everything from Mera terminal like khul raha hai to I don't know where should I write the program, I don't know where the figure is saved. We answered all of those in the initial stages, but they were also encouraged that look, all of these tools have built-in help, right? So you should learn how to use that help. When you make mistakes, it's at the end of the day a computer program. Nothing is going to explode. Nobody's going to, nothing horrible is going to happen. So try what you want to try. if you get an error, learn to read what the error is and learn to figure out how to fix the error. Because at the end of the day, you have to learn to do this on your own, wherever you go. That's the objective. Okay? So the focus was never on teaching them either complicated mathematics or developing very complex algorithms or writing elegant code. It was just develop a certain level of comfort with using computers for problem solving. The problems could be as diverse as your course curriculum takes you in the next few years. Okay? And we said that it could only be done in a lab course because they have to sit and do this on their own. You know, we can lecture them till we are blue in the face, but you become comfortable with something by doing it. Whether it is using an instrument, focusing a microscope, you know, drilling a hole, or using a computational tool. So they have to sit every other week for 3 hours, and you are only evaluated on what you've accomplished during those 3 hours. There are no take-home assignments, and during those 3 hours, discussion is permitted. Now you can go talk to your friends, you can talk to TAs, but at the end, go sit and write your own code. Okay, so that was sort of the philosophy and how the idea of the course developed.
So one of the problems that when we started teaching the lab that we found with the students was that many students, even though they are more tech savvy than us probably, still were not used to the idea of using the computer itself as a tool. I don't know if you face this problem in your classrooms, but we did face this problem, because if you are a programmer, for example, if you write some program, and if you get an error message, the normal thing that I expect that they would do is to read the error message, think what it is and fix it. Right? Especially in Octave, for example, it will say line number 17 and column 4, there seems to be a syntax error. What do you think the students do if they see such an error? No, if they call to the teacher, I would still be happy. No, our students were cleverer than that. They didn't stop. They did something else. They go to net. They cut paste the error message. So it is like you are talking to somebody in German, but you are using Google Translator all the time. If the person says something, you will put it there, you will see, then you will write your answer, you will translate. And once, I realized this because once a student came and told me that your Octave installation has a problem. I said, why? He said, I got an error message. So what? He said, I went to the thing, got some Slack something, and it says that your installation has to be changed. And that is when I realized that they were doing so, because of which we don't allow mobile phones and internet on the computers when we are doing the lab. So the first training for the students is to realize that if you are talking to a computer through a script, through a program, then the process is that you say something, and if the computer complains or says that this is not correct, you figure out how to respond on your own. You look up help files, you look up man pages. Of course, we do have the TAs and other students to talk to, but this was a big barrier that the students had to cross. And after this course, we also introduced a similar course for our master's students. In that case, I do know that the course has been quite successful, because I have colleagues come and complain to me saying that, oh, you teach in the computational lab, Octave and Matlab. The master students for their project are not writing programs in C or Fortran at all. They all want to do it in Matlab and Octave. So some of them did become comfortable with working with this, but that is one of the problems that we faced in the early stages. And several of us who do the follow-up courses, for example, I teach a simulation and optimization course, and I also teach a modeling microstructure evolution course, which is an elective. In the simulation optimization course, for example, we expect them to use the function calls from Octave to do optimization, as well as write their own scripts for solving some of them. Okay. Okay. So we do make them use these skills that they learn in the follow-up courses, which reinforces, so some of them find it to be useful later also. And in the case of master students, I do know that many of them become comfortable, conversant with these tools and start using them, even though, I mean, there are these things. Should we make them write programs in C and Fortran, or should we allow them to use Matlab? I think nowadays there is also a compromise. Something like Julia will give you as good as C probably, or only a factor of 2 slow, but as easy to write as Matlab Octave, so you don't have to worry about other things. But the reason why we chose was, like Professor Pant said, we wanted a software, and we also didn't want anything else to come in the way of students becoming comfortable knowing that they can work with a computer and solve simple problems. Okay, so that was the main purpose. And so this is the aim of the lab course, to expose students to computational tools for visualization, that is the first thing, numerical methods, that is the second thing, and data analysis. Okay, you will see some examples of some of the labs that we do later in this lecture. And the methodology that we decided to follow was to introduce to them the 2 tools. One was Matlab, the other one was Octave. Okay, and the introduction is done in one lab, 3 hours. Okay, and this material is also there, so I am going to share it with you in a Moodle. The introductory lab, for example, in Octave was a tutorial. It was written in a tutorial format. I want to show you that and discuss why or how. And please feel free to use this tutorial. I am going to share this in Moodle. So this is the tutorial, and this is how the tutorial starts. So it says something about GNU Octave. It's a high level language, it's a free software, and some information about where it is and why and things like that. So the first thing that we make the students to do, for many of the students, by the way, this is also the first exposure to Linux based machines. They don't know the command CD, they don't know mkdir, they are more comfortable, you know, with a mouse, right click, open a new folder kind of things. But to open a terminal, move to the directory that you have created, invoke Octave from that. So those are the things that they have not done, even though they have completed a C programming course, and sometimes they are not that prepared, or they have forgotten if they have done it early. Okay. So in this course, in the very first lab, we take first half an hour to 45 minutes to make them comfortable with these things, so they will note down everything. So open a terminal and then write CD, student desktop, and then create a directory with their roll number with that day's date, and that is where they will save all the work that is what will get evaluated and so on. So there is some amount of introductory Linux based working on the computer that they learn, how to open a editor, for example, gedit or something, and how to write, because Matlab comes with its own editor and run and things like that. But if they are using Octave, sometimes they have to do this, even though there are integrated tools that are available for Octave, but we do make them open a terminal, open gedit or notepad and write things and things like that. So after that, they will invoke Octave, and then they will check that they have got the proper version. This tutorial says, you know, open a terminal, type Octave and enter. Okay. They will do, then they will see something on screen that is given on the screen. When this part of the lab happens, I am also doing it on the computer, and this is getting projected on the screen. And I wait till everybody achieves this. Everybody should be able to see this. And we have about 5 to 6 TAs per session, and that works out to be 1 TA per 5 to 6 students. Okay, we take about 30 students in one go, and we will have 5 to 6 TAs who are available. Most of the times in the beginning, it is all hardware problems. My computer is not switched on, my mouse is not working, my screen, I have problem in, or it is flickering, or it is not working and things like that. But once that is settled and people know how to work with these machines, then the next problem is open a terminal, they don't know where to open a terminal. Okay. So we do give instructions, but in a class, you will always find that different people follow at different pace. Okay. So in the initial stages we are really slow, and when you are slow, the students who have already figured it out become impatient, and they also start misbehaving, they will be shouting, they will be doing lots of stuff. So because of this, what we did after I think first or second year, we sat down and wrote the entire tutorial. Okay, I'll show you the complete tutorial. And the first problem alone we will do concurrently. I will be doing it on the screen. I will do it relatively slowly. Students also will do it along with me. And that was just plotting sine function. Okay, that is the first thing that they do, plot sine x. So this is getting help. And then there are two modes of working. You can write scripts and execute them, or you can ask the interpreter to just do it as you are typing it in. So plotting sine x in interactive mode is the first exercise that I make them do. After we do, we make them write a script to plot sine x and cos x in the same plot. This is about 45 minutes to 50 minutes. After that, we don't teach. Meaning, we tell the students to read through each of these exercises and write scripts which will do what is there in the tutorial. And to help them do this process, we also tell, for example, the first script that they will write, let us say, so the plot is shown. So if you have to plot sine x, then they will see sine x, they will see what is there in the tutorial, they will compare with what they have on the screen. If it matches, then they are through, they will move to the next problem, right? And for each one, for example, using a script file, this is a script file. They have to type the script, save it, run it, and generate the figure. Once they generate the figure, they will go to the next problem. And the next problem is plotting more than one curve in the same figure. So you want to plot sin x and cos x or sin x and tan x in the same figure. So there is a script that is given which they have to write. This has the advantage that some students are doing it fast. They can do at their own pace. They don't have to wait for the instructor to introduce the problem. They don't lose their patience. And sometimes we have seen them walking out of the lab some 30 to 40 minutes earlier than the lab hour. Okay. And some of them go beyond 5 o'clock. I mean, sometimes we had a class after that in that same classroom, and that instructor, till he or she shows up, the students will not leave. They get involved, they are sitting there. And the advantage with Octave is that we also put this in the other computers in our computer room. So when they had time, they can come and do. There is no makeup for this lab course. And if they miss one, it is their responsibility to learn. All this will go into Moodle, so they will download even if they are not in the lab. They will not get the credit for not doing it in the lab, outside of the lab hours, but they can learn. If they have missed one lab, they can come and follow up on the next lab. But the responsibility of learning what happened in the previous lab is their own. Okay. And because it is written like this, step-by-step instructions, and the script is given, and the script is well documented, there are lots of comments, and what is the output that they have to see is also shown to them. And this tutorial is available with the students for the rest of the session, including the final exam. Because remember, in real world, it is never like nobody allows you to not to take a look at a book, not to take a look at some tutorial or some help file, and still you have to solve the problem. That never happens. So there is no reason for us not to test them under similar conditions in the lab course. So final exam also they have access to this as well as the help files. Of course, they can anytime help or man they can put and get the help to solve the problems. So this is plotting. And then we introduce them how to plot vectors. Okay, so this is a vector plot that they do. And many a times they have to plot by taking data that is there in a data file. So then we introduce plotting from data files. Okay. So they generate the data file themselves and then use those data files to plot, and plot in many different ways. For example, this is just data, then you want to run a line through the data, then you want to put an error bar on the data. So plotting with error bars is the next exercise. So once you plot with error bars, then you want to put legend, right? And if there is multiple columns of a given data, you want to plot different columns of the data, so that is taught. And more than one data file you have to manipulate and plot, okay? And how do you change the legends around? You don't want it on left top, right bottom, left bottom, okay? So there are exercises for that. And then there are handles that you give them. For example, you want to change the line width of the plot. It's too thin, right? So there are exercises to make sure that this line width is much thicker than the first sin x that they plotted. Okay, and how to save the figures in different formats, in JPG, in PDF, etc. So that is next exercise. Yep. So they come to the class, everybody's desktop has this file sitting on them.
But isn't it like we are just giving them the program they are running it?
Yes, because this 3 hours they get, and later you will see the kind of exercises we expect them to do from the second week onwards.
See, remember, this is the first lab ever. This is their very first lab. And they are starting from never having seen objects, never used it. And it is, I don't know if it may come as a surprise to you, it did take us a couple of times of teaching this to realize that even though these are engineering students in their second year, there is a huge distribution in their level of comfort at sitting in front of a computer and writing codes. There is a huge variety. So we could not simply say in the first lab, here is a problem set, solve it. Okay, and like Guru mentioned, that the other option was, don't give them the write-up, but we keep teaching them how to code by solving every problem on the screen. But then people who are at the head of this curve, they get bored very quickly. They will do sin x and legend and error bars in 20 minutes. And there is still those 20 students who are struggling with writing a simple 5-line code. And you are trying your best to take everybody along. So the advantage of having this was that those who are very comfortable can race ahead to the end. And we have no problems if people leave in, say, 2 hours instead of the entire 3 hours. But we still want to get those people who are still struggling at 5, when the lab is supposed to get over, we still want to get them to a certain minimum level. So for them, having this right up in front of them, be able to go back and forth, type, not get what they see in the write-up, compare line by line, and then realize, okay, this is my mistake. My brackets were wrong, or I missed a semicolon here. That helps them a lot. So it's a lot of hand-holding, I agree, but we've come to the conclusion that it is good to give this hand-holding in the early stages and then expect them to become fairly independent in the second half of the course.
And if you think about it, getting students who haven't worked with a Linux machine, who don't know how to open a terminal, and you will see at the end of this tutorial, they would be solving linear algebra and ODE in 3 hours. I have found that this tutorial is the best liked even by students who join our group, because I tell them it takes 3 hours for our undergrad, so it should take same time. One Saturday afternoon you sit and figure it out. After that, everything that they do in the lab, plotting or working with or doing simple computations, etc., should be done in no time. And this much of quantum of learning that happens in 3 hours is still amazing for me. And majority of the students, 120 students, we will also talk a little bit about how we evaluate this lab. Okay, so it is still, it looks like spoon feeding or hand holding, but it is not, because we are actually taking them and making them run pretty much by the end of the tutorial. Okay, so 3D plots and contours, okay, that is the next exercise that they do. Once they finish this, Okay. All this in 3 hours. So this is 3D plot with contour. Then they go beyond plotting. What are the things that we expect them to do? Do some matrix algebra, solve system of linear equations, and solve an ordinary differential equation. These 3 problems again in the same mode. Problem is given and you just have to solve. Okay, so you are given a matrix and want to find out eigenvalues, eigenvectors. So what is the command? How do you get? So you get all this information, right? And a system of linear equations. Here we do pick examples from things that they will tend to see in the department later. So this comes from mechanical behavior. So there is something known as Hall-Petch, which is this relationship. So there are 2 unknowns in this, the coefficients sigma 0 and k. That is what you want to figure out. So you are given data points. So you can, if you are given 2 data points, that is sufficient for you to get these 2 unknowns that you can pose as a matrix problem and solve it. So that is system of linear equations that you solve. And then there is, okay, so I don't know where the ODE exercise went. At the end, there are also these self-assessment questions which they have to do. So it's about 30-page tutorial. This they do in 3 hours, and the ODE is actually Newton's law of cooling. It just says that the temperature change with time is proportional to the difference in temperature. Okay, so it says that, okay, take a very hot ball, which is at 100 degrees, keep it in room which is at 30 degrees, how long does it take to cool, and what is the temperature look like as a function of time. So it is just dt by dt. This is the equation that they have to solve numerically, and there is a function call, so it's not difficult for them to do. So that is the exercise that they do. This is in 3 hours. So this is the very first lab that students do. After they do, the second lab is introduction to Matlab, and I think we have, do you want to go through the Matlab one?
So the Matlab tutorial is actually a lot more brief because they've gone through this octave tutorial, and like I said, for all practical purposes the 2 are identical, but in the spirit of making sure that they are comfortable with also using Matlab. So you know, the very next lab that they do will be a Matlab lab. I do tell them that, look, you've done an octave tutorial, most functions are the same. So in the tutorial is less detailed and the problem solving is more. Okay, and this is, you know, we just tell them that, okay, the Matlab interface looks like this. What does it mean? How do you work? So what they would see in on their screen, how they would get help if they want to use a particular function. What does it mean? What are the types of data in Matlab that they can use? And Matlab, the most usage that they would see is to work with matrices or vectors. So introduce them to matrices and vectors and then give them problems that, you know, what is this, how do you do the plot, and how do you create script files to do the various plots and so on. Again, 3D plots, and then there are problems. And I think there are about 7 problems. So the introduction to Matlab goes a lot faster, and most of the time they have to, so here is the detailed instruction that create 1 file for each of the problems, write a program and save that file. So at the end their folder has 7 programs in the second lab. And this starts with simple solve a system of equations, a program that does various operations on matrices, then do some centigrade to Fahrenheit conversion, so a little bit of programming, and then so problems 1 to 3 here the average student can do, I think, in about 15 to 20 minutes. These are fairly simple problems. Problem 4, because this is where they have to now start using a for loop, or they have to start using vector calculations fairly intelligently if they want to write a short program. this is where this, again this distribution of abilities comes in, that there are students who will write this program in also in about 10 minutes, and there are students who will take about 30 minutes and will ask the TA for a lot of help. Instructions to the TAs are that they can give as much help verbally as they want. They cannot sit with the student and write their program for them. Not a single word should be typed by a TA, because do this, when the students do this, they remember कि ये type किया था. Okay, so problems 4, 5 and 6, I think 5 and 6, and here again we say they write a function. So we move now from scripts to functions, and then say write a function, then you call the function. So we introduce all of those and they become comfortable with that, and then surface plot and so on. So problems 4, 5 and 6 will take them anywhere from about 45 minutes to 1.5 hours. So this is their second lab, and now we assume that they're comfortable using both Matlab and Octave, and then we switch to the actual problem solving, right? Yeah, these are the exercises.
After these 2 sessions, the remaining session is for those.
No, you have to use this.
One is fitting, the other one is data analysis and fitting. Those 2 examples I am going to show you to tell you what is it that we exactly do. And then one on ODE, PDE, where they will solve some heat transfer or diffusion problem. And then there is a last lab that they do is almost like a mini project. Okay. Sometimes we make them solve the 3-body problem, because that is still a set of ODE equations. So sun, moon and earth, how they go around, there is the relationship about the attractive forces, and now you have to solve the ODE, Newton's law, to find out how the 3-body system is moving. Okay, so that is, for example, done in 3 hours by students who started without knowing how to open a terminal. Okay, so to that extent we are really happy about the way this lab progresses. And I wanted to give you a little bit more detail on fitting and the data analysis lab that we do. All this material will be shared with you on Moodle. So let me show you the fitting lab. So it is also written in the same fashion. Everything is spelt out, and the first problem, that is lattice parameter variation with composition. So unlike the examples that Sachin was giving, in our cases, in all cases we know what is the physics. For example, we know that lattice parameter with composition is linear. So it's only a question of fitting the linear fit. And linear fit is just a special case of polynomial fit. Linear, quadratic, cubic, or 4th order function, 5th order function, everything you can fit just by calling polyfit, which is one command. So this is what we introduce in this problem. Okay. So this is a linear fit. Again we give them the data, they are supposed to enter the data, they are given a script, so they will write the script, they will do the fit, that is the data and the line that they fit through, okay, and they will save this figure. Now there is a special case, so we introduce them to the next difficulty level. Sometimes the fitting is not a polynomial. It is AT plus BT cube. We know that specific heat at very low temperatures, for example, will follow this rule. Or at higher temperatures it will be A plus BT CT power minus 2 and DT power 2. Okay. And in those cases, for example, if it is AT plus BT cube, your fitting should not give you any intercept at all, right? And the T squared term should not be there, we already know. We don't need to do the analysis from the physics, we already know that for this data, there is no T squared term that should appear. But if you generally fit a polyfit, it will give you those coefficients also. They might be very small, but it will give you. So in order to avoid that, you have to use, and Sachin showed the derivation of that. So this is known as a design matrix approach, and that is what we do in this exercise. I'll show you that in the presentation. And then we give them another problem. Okay, so this is the data and that is the fit that they make. Again the files are given, and then they are given questions So, these are simple self-assessment questions. Then they have to do exercise. And we also teach them about one more problem where the problem is not linear, like some Arrhenius, some a equal to a naught exponential minus q by RT kind of things, which you can take logarithm and turn it into a linear problem and solve it using polyfit. So, that is also given as one of the exercises. So, they have 3 exercises to do. Again, it takes about 1.5 hours for some of our students, and some of our students finish early in about an hour or so, and then they leave. So, that is the second exercise. And let me go back to the presentation. Okay. Okay. So, here is something about the evaluation scheme, but before that you want to go through the data analysis part? Okay. So the evaluation scheme for the lab is as follows. They do 6 labs. Each lab session is 10 points, and the most important thing is that marking of these labs is liberal. All that we are looking for is that the student tried to spend the given 3 hours. Many of them would have completed, about 60% or 70% of the lab would have completed all the exercises. Some would have taken 2 or 15 minutes, some would have taken 3 hours. Some even after this would not have completed, so some 20% will be left. We don't punish them too much. If they have completed 80% of the lab, they get 8 points. If they completed 90%, they get 9. Most of the people would have gotten 10 on 10 on each of the labs. Then there is one final exam. We are also sharing with you one of the example final exam papers that we have given, where they are given a set of problems. So, they have to write 4 or 5 scripts to solve these problems, 40 marks evaluation, and so the grading is on out of 100 based on these marks. Okay. So, they are not punished for not getting the answer, or not even, if they are not completing it, they are still not punished very badly, right. Most of them will be between 80% and 100%. Okay. So, that is about the evaluation. So, this I have described. So, we solve linear and problems that are not linear but can be turned into linear, and polynomial. Linear is just a special case of polynomial, and specific fit. So, these are the things that we do in fitting. So, this is the third lab, Octave, Matlab, fitting. Next one is where we also introduce a little bit of data analysis. So, that I will so, the design matrix, I think this Sachin has already explained how to do. So, I am going to skip that. So, one of the things that you do after doing the fitting exercise is that they also should learn some of the good practices, and I insist that all problems that they solve, the data and the fit that they make will be plotted on the same plot. So, every exercise that they have to do. And sometimes here we also tell them that you do a plot and you fit, and then you see the plot, and there is one data that is sitting outside very far from the line. Okay. Sometimes this can happen because they entered the data wrong, because they entered the data themselves instead of 0.13, if they type 0.31, then they can see something like that. So, we make them, and the students will also see that they have also seen my plot, and one data is far away, then they will wonder why, they will go look at the data file and they will correct it. Okay. So, this is a good exercise, and sometimes I also tell them that sometimes you will genuinely see data points which are far away from your fitted line. This can happen. In those cases, you should not touch those data points, or if you leave them out, you have to explicitly tell people that there was one data point which was lying like this, and we have removed it from our fitting exercise. Okay. And we also insist that they pay attention to the fitting coefficient. In many of these cases, it is physical, so it has a meaning. As you will see in the next exercise, one of the fitting coefficients is the Young's modulus of the material. So, they have to pay attention, and it should be in the right order and the right number. So, if it is not, then they also know that there is something wrong with the fitting exercise they have done. So, these are some of the things which we discuss as they are doing. I mean, it is not like completely we are off. One problem we will do on the screen and they will do, and then the TAs will be around, and we will also be spending time in the lab, and once in a while we will have some discussion. And sometimes if I find that everybody is making the same mistake, sometimes the TAs will come and tell us that there is this issue, many of them did not get it, then you go to the board and do only that portion for everybody and leave them again to go back to their problem. Okay. So now I'll.
Okay, so this is lab 3 typically, and then the next lab becomes interesting. So what we do is, or becomes more rooted in reality, because what we do is, we now give them experimental data. This is a lab which they would typically do in their 3rd year. So we tell them that, look, your seniors did the experiment. The experiment is actually very simple. I think those of you who are from civil or mechanical or metallurgy or aerospace would know this experiment. It's a tensile test. You essentially take a sample, which would be a strip of metal or an alloy, and you pull it in a machine which will simultaneously record the load applied to pull and the elongation of the sample. Okay? It's a fairly straightforward experiment, and it gives some very, very useful physical properties of the strip that is getting pulled. Okay? Nowadays, because all our instruments come with computers which have loaded upon them software which do this analysis for the student, we also tell them that, look, when you do the experiment, then in fact the software will do the analysis and will give you the results. But we want you to think back on how these results have been obtained. So we take data from an undergraduate lab. So this is what raw data is like. That's being generated in an experiment. So you see load here, and that will, ideally it should only increase, and it says the load is in kilonewtons. But if you pay attention, you'll realize that the load sometimes increases, it increases, but then it also goes down here, because this is an actual experiment and instruments are liable to be noisy in data recording. So this is the data. There is load, there is elongation, and then there is stress and there is strain. Now what they actually need are these two quantities, this column and this column. Okay, so we show them this and we say, look, eventually all your analysis has to be on these two columns. Now the first instinct will be, well, let's open it, let's copy these two columns, let's paste it in a separate file, and let's work with that clean file. Also, if you see, the first row is a header row. If they write their program to start reading data from row 1, then they'll get an error. So the instinct also is, let's delete that. But then you remind them that, look, that the software that is attached to your machine is not doing all of this. It's taking this and it's able to work with this, right? So start your program such that it knows that it has to read data from row 2 onwards and data from columns D and E. Okay, that's the first set of instruction. So you have to do your write commands accordingly. And what they have to calculate from this, so I'll just draw you a schematic of what it would look like if they were to plot this. So we would plot stress here and we would plot strain here. I mean, we take this again because, like Guru said, this is something we know they will see and they'll use this a lot. And they see this in their theory courses from, I think, first year onwards. The initial part of this is expected to be linear because this is elastic deformation. And the slope of this gives you something which is called the Young's modulus, or it is a measure of the modulus of elasticity. Okay, for those of you who are from not mechanical, metallurgy, etc. background, if you imagine solids as being made of atoms which are connected by springs, in some averaged out sense, this is a measure of how stiff those springs are, how difficult it is to pull them apart or push them together. That's what this quantity is. Okay? So the exercise they have to do is, it's conceptually very simple. It says, well, this is your data. When you plot it, it will grossly look like this. You fit a straight line to this initial part of the data, get the slope of the line, and that's this thing called Young's modulus. Okay? And in doing this fit, you will figure out till where is this plot linear. That is some another physical quantity which we call the yield stress. And then you figure out the maxima of stress and you figure out the maxima of strain, and those are things you can just read from the table. The challenge lies in first the nature of the data. You look at the stress versus strain column E. That strain column reads 0, 0, 0, 0, 0 while the stress is still increasing, right? So what this is telling you is that you're applying a load, but whatever strip you're trying to pull is not getting pulled at all. Now it could actually be that this load is insufficient to pull the strip, or it could simply be that whatever is measuring elongation does not have the sensitivity to measure such a small elongation. And experimental data will run into these problems more often than not. So they need to appreciate that experimental data is noisy, the numbers fluctuate, the numbers can be zero at times. So when you write a program, your program should be clever enough to take those things into account. The first instinct is to say, well, I have to calculate a slope, right? I know from my 8th class algebra that it is y2 minus y1 divided by x2 minus x1. Now you try to do that here, you are dividing by 0 minus 0, so you get an infinite number. Doesn't work, right? So you tell them, well, take a look at the data, see that it is often 0, put a test in your program which will eliminate all such rows where one or the other value is 0. It's unphysical, so get rid of it. Okay? The second challenge, of course, is, well, where does this linear part end? You're trying to do a fit, right? You take very few data points and it's not a representative enough fit. You take too many points and your straight line fit will go like this, right? So they have to now develop an algorithm which will start reading data, start implementing some strategy to figure out where does this linear portion of my data end. Okay? So, and we just leave it at that. We say, you know the problem, you're familiar with stresses and strains and what they look like, you know the initial part is linear, do it. And again, we allow them to have discussions with whoever they want. They can walk around in the class, they can talk to each other. What they cannot do is copy somebody else's program. It is okay if 4 of them come up with an algorithmic solution together, but each one has to then go back and implement it individually. Okay? And this takes a good 2.5 hours. This part they keep, you know, and then we throw the next zinger at them because some of them are clever enough. You know, if you give them one data file, they'll hard code the properties of this data file, right? They'll open it, they'll say, okay, the first 80 rows are 0, so I'll start reading from row 81 onwards. And they'll plot it, and they'll say, oh, I have seen that this point, it occurs at about 150. So I'll hard code that, you know, if y greater than 150, then whatever. Then you say, aha, remember that software that is preloaded with your machine? It works for every material that you put in, right? So your code should be at least as good as that software. So they have to write one program and we give them 2 sets of data, aluminum and here it is brass. Similar thing, and we say that, oh, here the rest of the quantities are not even calculated, okay, sorry. But it's similar data and we say that, well, write a program where the only thing that you will change is the name of the input file, and if you develop a general enough algorithm, it should work for both. And we also give them that what are these quantities. This is aluminium and brass. We know what the slope of this region should be for aluminium and brass. Some of them also know. You know, they've read it in their textbook. So we say, look, you know that the slope should be somewhere in the 100 to 150 range, or you know that the slope should be in the 80 to 150 range, right? But 80 to 150, remember the units. Then we also remind them that each of these quantities have units, and when you're doing A over B, you should remember the correct units, otherwise your numbers are going to be off. Instead of megapascals, they're going to be gigapascals and so on. So they kind of know what the right answer is. They can test their code themselves. If it's giving them the answers in the right ballpark, then they've got it. Otherwise, they have to keep tweaking their code. And this keeps them busy for the entire lab. And I think we've had some students who've come up with fairly innovative solutions to where the limit of this linear region lies. So I think we will also upload these data files. I'll make sure that the two data files look similar, and if you like, you can use it to design your own lab experiment. Like I said, we've picked experiment from metallurgy and material science because this is similar, but it should also be okay otherwise. So no, we can actually now. So I think we're. Yeah, this is okay. I think, can we show them, let's show them the exam paper first and then we can come to the takeaways. Yeah, so this is the exam paper that they have, that Guru was talking about. It's 1 hour 20-minute exam. All the instructions are there. We say you make a folder, save every program. For every question you write a program. And so there are simple numerical problems where the equation is also given and they just have to write a code which will take an input and which will solve this equation to give the answer that we want. We ask them a plotting problem, a mesh command, a contour command, contour 3 command. And remember, we've been trying all along to teach them how to use help or manual pages and so on. So once we given the command, if they can look up help, they can do this fairly easily. And then the last is this fitting problem. This is the example that we were showing you. Data is given, do the fit, do the plot, and tell us what the fitting coefficients are. And yeah, this is a marks distribution and they have to do some calculations. Yeah, using Python. So I think one of our colleagues started teaching Python after we did this thing. So there is also a Python problem. So 4 problems, 10 marks each, 40 marks paper, 1 hour and 20 minutes to do these many problems. That's the exam paper. Yeah.
Almost like you wrote down the question paper and you started teaching them so that they will be able to practice.
So I think we have pretty much given what we wanted to give, but we would like to hear from you. Questions, concerns, comments. Yeah. So there are TAs. The TAs will go through. No, without TAs you cannot run this lab. First thing is, every class I need TAs. Because 30 students, if all of them raise their hand together, I cannot handle that at all. The lab works only because we have rows and every row has 2 people. At best there will be 2 people with raised hands who did not get help. Then we will go talk to them.
Like you said that there will be some students who will be having a faster pace than others.
Right.
So what I do that I tell those students, I target them and I ask that you help the ones who are falling behind.
Yeah. But in our classrooms that happens automatically. Because among themselves they know and we allow for discussion. So you will see these 2 kids for whom they will always go have a discussion, come up with an algorithm and things like that. But we don't actively promote anybody in the classroom. If students go talk to somebody and get help from that person, that is allowed. But as an instructor, I will not say so and so will help. That's only TAs. Yeah. Yeah. So at the end of the lab, everybody's directory will be taken and the TAs will go through. If there were 20 problems in that tutorial, and like I said, 5 students is 1 TA. So 5 into 20, 100 problems the TA will evaluate for that week. 8 hours per week is what our TAs are supposed to do the work for, and they will sit down, go through every code and give marks for each problem, share it with the students, and if the student complains that it is unfair, they will even answer that question. Why they did not give marks, especially in the Matlab one, where people can come up with new algorithms and new ways of doing things. So you still have to take lots of judgment calls, and they will even justify those to the students. So it is the TAs who evaluate. Without them, we will not be able to run, and for several years, me and Prita will give a party to the TAs at the end of the course. They were asked, and the first day the students are told, the TAs are teachers in this classroom, you will treat them exactly like you will treat me and her. So, and they are seniors maybe, but in the classroom, the interaction is different. They are teachers, and these are students.
Actually, I take a lab. So back strength is around 25 to 30. So what I do, I take actually AutoCAD based labs.
I see.
Civil engineering department. Eventually, what I have to do is that, okay, you will draw in these 3 hours. Whatever your problem is, you ask me, I will personally help you, each one of you. And then finally, before the starting of the next week's lab exercise, you have to submit a hard copy. So that I evaluate later.
But can't you ask them to save their drawings onto the computer and then
Again, I have to personally open each and every computer personally, 30 computers, 30 folders.
Yeah. We have help for that also. There is a technician. Yeah.
Initially, you stated that regarding the online help.
Correct.
What I feel is that, okay, initially we should not allow them to directly copy paste to online Google or something. That you should not do directly with the initially you should try. But like you have 8 labs or something. If there are 8 exercises, then at least after 4 or 5, 4th or 5th one, they should be allowed that, okay, you go access whatever you want.
No, it is dangerous because 3-body problem, if you go online, you can download 50 different Matlab codes. That's not what I want them to do, right? They will go out and when they are working, probably they will use somebody else's code. But in the lab, I want them to develop. So this rule is only for the lab time. Any help is only from the man or help or the tutorial that is available for you.
So see, there's another problem with that typing things into this thing. Students actually don't stop and think. The error, like Guru was saying, okay, it will say line 23, column 4, mismatched bracket. Now this is plain English, right? Go to line 73, go to column 4 and see that you've got the wrong bracket. Now, you need not know that, okay, which is the right bracket. Just try a few different ones. That's the advantage of doing things on a computer, right? It's hopefully not going to explode in our faces. So if square brackets are not working, try curly brackets. Try rounded brackets. If they figure it out like that, then they're likely to remember. Right? If they copy this, paste it in Google somewhere and Google will say do this and they will do that, they'll always want to do that. So the idea was, just learn to read and interpret.
Yeah, but there is another lab, which is a design lab. In that lab, they are allowed online access, but they are given a design problem. So the data is what they are supposed to access online and come up with a solution. For example, it might say this is a furnace. What is the wire you should use for heating element? You go online, look up whatever material and find the specification and justify your choice by saying I chose this material because this has these properties. So it's only for this lab, only for these sessions we have this restriction because we found this to be the problem, especially these codes. For example, simulation optimization also. My own codes are there online, right? So I can't allow them because then it is not a learning experience for them. Wherever there is other types of data they have to look up and answer, they do allow. I mean, I have colleagues who do allow internet access during the classroom, but not in this lab. Yeah. Somebody had a question there, I think.
after a while, like if I am teaching that person, I have taught them ABCD, and the curious ones will go online and they somehow will find out that MLOP is also there.
Right.
I can use them and it will make my life faster.
Right. Yeah. So if you want to have different gradation in the class, yes, that would help, and you can allow. But because in our aim is to take all of them, and we have TA help again and again. Without TAs, active learning will not work for me.
Hello.
Yes.
Is there any way to do it without me?
Is there a way to do this without TA?
Are you not allowed to use your, suppose you teach, you're from which department? Civil, okay. So suppose you've taught second year students this year. I guess you can't ask those students to come and help in the lab next year. You'll be having a different lab at that time.
They have different labs.
Okay. I know. So if you don't have TAs, the only way you can run such a lab is by peer instruction, right? The one thing that we have tried, and we have done it in the past, and I think that goes back to think, pair, share kind of things, is that we used to put random groups. Every lab, there will be a new set of students and they will all get problems, and the problems will also be not identical. Slightly modified problems to each group, and the group has to solve the problem. You will randomly choose the person in the group to ask questions. Evaluation is based on who you pick randomly. So it's not possible and the entire group gets the mark based on that. Okay. So even if the clever student solves the problem, it is in his or her own interest to teach it to everybody. Okay. So that is one way probably I can think of that you can make it active. Group based, peer based learning and evaluation schemes will force them to make sure that everybody learns, not. So sometimes I do have a problem, because if the instructor starts identifying some as clever students who will help others, that can lead to kind of dynamics in the class that you don't want. Sometimes, I mean, I'm not saying it's always. So and TAs have a stature, like she said, if you can get the senior students and do, that is still better than picking from the same lot. But this one, making into groups, but random groups. We used to have a program which will every class randomly allot students and give a group, and using the groups we used to do the tutorials and random problems, and again evaluation is by you pick somebody and say whatever that person's answer, the entire group gets the mark. So everybody will be at the same level in every group. So that works. Anything else? Yes.
I'm taking this lab in my college, and I feel there is a problem, which is not based in the language lab like C++ or it is that theory course and the lab both are in the same semester. So they learn the syntax and all in the theory class, and then they perform. But MATLAB doesn't get a theory class. So when I am taking their this first or second term, then they say that we don't know the syntax.
Right.
So that's why we have to handhold them and give them the programs.
So the best I found is to write a tutorial or give a book like Rudra Pratap's Introduction to Matlab, which has all commands, all information, or make a cheat sheet out of that, give it to them every class, let them have it, and knowing the commands and with the help file they should be able to do. But I mean, the whole point behind MATLAB is that they should not spend too much time in syntax, right? So give them only the minimal help.
Take the first two labs, if you take them very slowly, you'll find that they become independent more quickly. What I've also done in some of these labs is that I say, okay, I say that, okay, we will start. We say, okay, MATLAB takes, you can have numbers, you can have matrices and vectors, and you can have symbols. And you
write small programs to solve small problems and pause after every this thing and say, okay, now here is a problem I have solved. Now you go ahead and write your own code. And wait till every last question is answered. Okay? I mean, in the first lab, every question is allowed, however silly that may be, and however many times it is repeated. But what I've found is that if we do that for 1 or 2 labs, about 60% students get it. After that, they can write on their own and they can focus on other things. And you can then give them more complicated problems and say, okay, now focus on the problem solving because you kind of know the syntax. Also, really, it helps to encourage them that how do you use MATLAB's built-in help? See, MATLAB even has this whole function directory, right? So I spend a lot of time saying this is how you look it up. I even tell them that I often don't remember syntax. You know, so I remember there is a function like this. I roughly remember that this is what it does. I never remember the details. So you just go look it up.
And peer help is very good. You allow them to talk to each other. That also will reduce your work a lot because somebody figures out and they will always share the information with their friends. So that also helps in bringing down your load.
No, I just want to say something about your question because I also teach a lot of computing in the courses that I teach. See, so I completely changed from teaching syntax. So initially when I started, I was in IIT Madras before I moved here. So there I used to take some classes on. So there earlier it was C and then we moved to MATLAB. So we used to have some classes on teaching syntax, for loop and while loop. And even though they have done it, I thought I should teach them. But then slowly I realized that, this sessions of teaching syntax doesn't take me anywhere. Neither me nor them. You don't go anywhere. Then, see, the best way of learning a language, okay, is, see, we human beings innately have ability to learn a language without being told anything about grammar. My parents never sat with a grammar book. Yeah? I just picked up grammar looking at what other people were talking. And this is our natural style of learning. We can learn very fast from examples. Yeah? Our kids copy us in 2 minutes, right? They just observe us, they just observe other people and that ability, I don't believe that, that is only up to age of 6 and all that is. You keep copying and keep learning things. So what I do nowadays, when I teach, I say that this is a problem in thermodynamics, okay, which I have solved like this. This is my code. This is another problem in fluid mechanics, which is very similar. Your job is to look at my code, write a program to solve this problem. People know how to copy, learn from so my program has all the elements. It has, display a file, for loop, while loop, all those things are there in that. Okay, they implicitly learn the syntax when they are solving a real problem. They have a real problem to solve in some fluid mechanics. That is related to something. And then you pick up the syntax on the way. Okay, and that is much more quicker than, if you spend some time in the beginning talking about syntax, it takes, none of us go anywhere. Okay, so just throw them in water. Okay, and we are very good at, doing this when you are thrown in water. Okay, so this is what, I keep telling even my PhD students, MTech students that look, see this our education system makes us believe that everything has to be deductive. Okay, some general principle has to be taught, then you apply it. But that is not how we learn, We learn scooter not by taking some, did you learn cycle by taking some, I mean, you start driving it, you fall some 5 times, then 6 times you know how to do it. Yeah, so and then in programming, what Prita is, rightly saying, there is huge help. I don't remember all the commands. I don't even remember, 0.01% of commands of MATLAB. Help is there, you just say help, it will give you help. You have to build this confidence. What is important is not the syntax. Building confidence in them that they can search for it. Look for it. What is there? Just look for it. It's all. See, what I tell them is, look, there are demo programs of MATLAB available in the MATLAB toolboxes. Open the program and copy it. In the exam, you have entire demo program available there. Just look at the demo program. Who is stopping you from looking at a demo program? So you are clever, you can do it. What is that? So I think we should, the active learning, is more of throwing them into water, making them do things and then learn from that, rather than, it's not about the tools, it's about, making them learn that you yourself are able to pick up things if you are, so that is more important. I think that works quite well. Now just throw them into water. Yeah.
And it works for everything. For example, interns in my group get a model LaTeX file, and even undergrads finally prepare their report in using text. I have another intern now who copied a demo problem in Phoenix on some the thermal expansion problem, and has modified it to solve a problem that is of interest to us in a week's time. So giving an example and learning from that works for everything. And that I don't consider as spoon feeding. I mean, that is the right way. Make them do, and you keep increasing the difficulty level. Don't keep the same. I mean, you just keep bigger and bigger challenges. Many of them will rise to it. So
no, and see, just look at yourself. Don't you keep learning from what others are doing? There's so many things. Yesterday, Professor Verma was telling that he learned from his seniors. So this learning from others doesn't stop when you are just grown up after being a kid. See, we learn by observing others. We intelligently modify it. We don't copy it in toto. That is our strength. So I think that ability has to be nurtured. That, and if you there are bottlenecks. There are so at each level, and I understand that for us to the resources that we have and the resources that you have, there's a huge mismatch. So at one point I was going to say that the way we are talking is like, what the Queen Mary is supposed to have said, no? Yeah, they don't have bread, let them eat cake. So maybe we are saying that. But having said that, it's about the attitude that you can bring in by making students do one thing by doing an activity. If they are freed of this fear of trying, fear of doing things on their own, then see, what is important is that not to teach the entire course like this, not to do. If you teach them this method, that you can learn yourself like this by failing, by trying. Then and if they get introduced to that, that is important, because that is a real survival skill. That's a real survival skill, that you can learn yourself by failing, by trying things, and that they already have. See, all of us learn from examples by doing, by So it's only that we have been told that unless you read some book, pass some exam, and till then you are no good, which is wrong. All that you want them to realize is that you can do it yourself, you can learn, you can make mistakes, and do it and then learn it. So that method has to be at least introduced, as against all these deductive things that we do, mug this, solve this problem in this particular pattern. So once you introduce this method, to them, hopefully many of them will just catch it up and, develop better. Okay, thank you, and thanks for your patience. Let's thank both of them for a nice presentation.